In our last lecture, we talked about one possibility to resolve the contradiction that we had observed between the density of the universe and the geometry of the universe when it came to deciding the fate. The density said that we lived in an open or coasting universe where we would expand forever because the density was much less than the critical density. But observations of the geometry said we have a flat geometry and therefore that we live in a critical universe, and this could not be reconciled. So people tried to improve the observations of both the density and the geometry. And the way you would improve your studies of the geometry is to have better distance measurements to galaxies. You probably remember it's kind of tough to get good distance measures to galaxies. We need things like that are standard candles, and before we started using white dwarf supernovas, we didn't really have good standard candles. Our best choice prior to this was to use the Hubble law. But the Hubble law had a problem because at that point we didn't really have a good sense of what the Hubble constant is. By now we do, but at that time we didn't. So studying the distances to galaxies was really important for a variety of reasons. It would help us narrow down what the Hubble constant was, and it would help us study the geometry. And it was in the 1990s that scientists first came up with the idea of using white dwarf supernovas as a standard candle. And it turns out that white dwarf supernovas give really, really accurate measurements. You have to be lucky enough to find one in the galaxy that you want, and that requires a lot of monitoring and keeping an eye on things. But when you find one, you actually can get a very accurate distance measurement. And these things can be seen in very distant galaxies. In this particular one that you're looking at here, there's actually 3 different white dwarf supernovas happening in this galaxy. That was, but you can see they're different years, 1999, 2007, 2008. So this one had pretty much faded by then. But these were supernovas in this galaxy. And so this started giving us better distance measurements, and it gave us ways to look at the geometry. Now, what they do when they're trying to decide the geometry is to take the data about the distance to these galaxies with the white dwarf supernovas and try to fit it to various models. On this particular graph, you don't really need to understand what's on the axes or anything, but you can see that they have drawn what we would expect these data to look like in each of the 4 models we're considering: recollapsing, critical, coasting, and accelerating. And you say, which of the models seems to fit best? Now, these galaxies in here where you see none of the little horizontal lines, we know their distances really accurately. That doesn't help us narrow things down very well. But as you start going to these further and further away ones, these are more and more distant galaxies, you can see recollapsing is just ruled out. We've already said there's no good evidence for recollapsing. Supernova data just rule it out completely. The critical doesn't look so good anymore. Before, the geometry had said probably critical, but this is saying the critical doesn't look too good. There's not too many points on this green line. The coasting looks okay if you consider the amount of uncertainty in these measurements, which the little lines tell you about how uncertain the points are. They could be anywhere along the little line that goes through them. Coasting might work, but if you wanted to pick the line that fits best, the one that fits best is the accelerating model. The line of best fit for the supernova data is accelerating. Now, before, we had ignored the possibility of accelerating because there wasn't any evidence for it. You need really, really strong evidence to even consider the accelerating universe because it requires this mysterious unknown force that we don't know what it is that causes the acceleration. Now, all of a sudden, we have data that support the accelerating universe. And that resolves the contradiction because an accelerating universe can have any density and any geometry. So it's possible to have a flat geometry, a density less than the critical density, and this accelerating thing all in one model. It brings everything together. So if you believe these supernova data, then we have pretty decent evidence that we live in an accelerating universe. In fact, this is so significant that the scientists who discovered this actually won the Nobel Prize in Physics this past year. It's that important. So this was a huge, huge, huge discovery. So what we are left with as far as the fate of the universe goes is we live in an accelerating universe if you believe the supernova data, and most astronomers do. It does imply that there has to be a force causing the acceleration, and we really don't know what this is. This is quite possibly one of the two biggest questions in all of physics right now, and certainly I would say it's the biggest question in astronomy right now. We don't know what the force is. We call it dark energy. Dark energy is kind of a meaningless term. It's sort of our way of saying, we don't have any clue what this is. But it does resolve the contradiction, and it fits the supernova data. So right now, the majority of astronomers would agree that the fate of the universe is that we will not only expand forever, but that the expansion is accelerating. So you can almost imagine that we live in a universe that's going to end up in a big rip. There's kind of one funny thing about this, just as a side story to end with. Back when Einstein came up with the theory of relativity, he did some math and you solve various equations and sort of try to see what does this imply about what we would observe. And Einstein did some of this math and he discovered that there was a solution to his equations that worked, that fit all of his math, but that it implied that there was this mysterious unknown force that would cause the expansion of the universe to accelerate. Now, Einstein didn't even know the universe was expanding. He was doing that work before Hubble did his work, so he didn't even know that. So he got this result and said, this is ridiculous. This is the biggest mistake I've ever made. He had done his math right, but he said, this is just completely ridiculous. You just have to completely ignore all the work that I did on this math because it implies something that's not even possible. Then it turns out that, well, guess what? We live in an accelerating universe. Einstein's biggest mistake, he seriously, literally called it his biggest mistake turned out to be right. So even in the thing that he thought was the worst mistake of his life, Einstein actually turned out to be right. So if you're ever thinking about your own mistakes, maybe sometimes you can think about Einstein, and sometimes those mistakes turn out to be good things after all. And with that, we conclude our lectures on astronomy. Congratulations, you are through.